take a look at some of these new sections on geometry. So we'll continue to review over the next couple of days. And the first section, 15.3.1 and 15.3.2 deal with a lot of things related to triangles. So one of the ways that we can classify triangles is in terms of the number of equal sides. So you can have a triangle that has all three equal sides, and we call that equilateral, 3 equal sides. The other important thing about triangles is that if you have 3 equal sides, then the angles opposite those have to be the same. And every triangle, when you add up the 3 angles of a triangle, you must get 180 degrees. So if you don't recall this, I will share a couple of the results. The sum of the 3 angles of a triangle sum to 180 degrees. Now, it turns out that also in a triangle, if you have 3 equal sides and you have an equilateral triangle, then the three angles also have to be the same. So an equilateral triangle would be 3 equal sides. So that means 3 equal angles. And if all 3 angles are equal, and when you add them together, you get 180, then you can deduce the measure of each one of those angles. The next one is isosceles, and this one would have 2 sides are equal, and the third side is not equal. And then finally, scalene have no equal length sides. So all 3 sides are different lengths. So these 2 pens are the same length. Yeah? So if I put a pen that's a little bit longer, this is isosceles because we have these 2 sides are the same. And this one's a little bigger. If I get another pen like this and put them all together, these 3 pens have the same size. So here's your equilateral triangle. I can get it on here. All 3 sides the same. Notice this one here would be a little bit longer, so I would have to widen this a little bit to make this one. This one's isosceles because we have 2 sides that are the same and the third one is not. And then finally, here's my third side. If we have 3 sides that are all unequal, we can certainly form a triangle with those. There it is. And this is called scalene because none of the sides are equal. Okay, go ahead. This is just 4 problems on here. Just circle the kind of triangle that you see. If you think that there's 2 equal sides, like for me, it looks like this side is equal to this one, I'm going to put a little mark on there to indicate these 2 sides are the same. I'm not going to put a mark on here because that side's different. Or if I do put a mark, it'll be something to say that it's not the same as the other 2. So every one of these triangles, there's 8 of them on here. Every one of them are either going to have no equal sides, exactly 2 equal sides, or all 3 sides the same. So this one, since it has 2 equal sides, is isosceles. Let me label them here, A, B, C, D, E, F, G, H. What do you think about B? You want to answer? Go ahead and put your answer in the chat. Okay, good. I would say that those 2 sides are equal, and this one is not, isosceles. What about C? Ideally, you want to get your ruler out and measure and try to see if they're all about the same, or if they're different, like about 1 3/8, 1 3/8, 1 3/8. Yeah, okay, I agree. Equilateral, all 3 are the same, so we would put the single marking on all of them. This is a right triangle, looks like a right triangle. Usually for a right triangle, we'll put a little box in the corner there. We do know that in a right triangle, the hypotenuse is the largest side. And since it's the largest side, we do know that it's not equal to the others. What do you think about D? Okay, good. That side is not equal to this side, and those 2 sides are not equal to the other one. So usually we'll put different markings on each side. Scalene. Okay. You have the other ones done? This one, isosceles, it looks like these 2 sides are about the same. You know, we'd probably want to measure them. Same thing here. These are isosceles. 2 sides are equal, but not the third side. This one equilateral, all 3 sides the same. And this one is, looks like another right triangle, but all the 3 sides are different. Now we can have a right triangle where these sides are the same, and we would call this an isosceles right triangle. So a right triangle can be isosceles, or a right triangle can be scalene, but it cannot be equilateral, because if we have an equilateral triangle, then all 3 sides have to be the same, which means all 3 angles are the same, which means all 3 angles have to be 60 degrees. And the definition of a right triangle is that the biggest angle has to be 90. All right, so classifying triangles, you'll be asked to do that. Okay, similar triangles. We have a result, from, and these are broken down like this. All right, so again, you have 8 problems on this one. These are numbered, and they tell you that these triangles are similar. And what that means is that the 3 angles here are equal to the 3 angles here. If the corresponding angles of 2 different geometric shapes are the same, then you have what we call similar triangles. So I'm going to say it this way. Corresponding angles are equal. See that triangle there? Pretty big on your screen, right? Let's say we measure these angles, and we saw that this one here was 50 degrees, and this one here was 50 degrees, and this one here was 8. This looks a little bit, let's say that this one's 90. Well, I don't want to say that it's 90. But, well, we could say let's say it's 92. And if that's 92, then that means we have another 88 degrees left over. So these two then would have to be 44 degrees. So 44 plus 44 plus 92, 44, 44, 88 plus 92 adds up to the 180. Now, what you're going to find is that if these two angles are the same, then their opposite sides are the same. So for this 44, if you go opposite it and you see 6, then if this angle is 44 also, this side over here also has to be 6. All right, so now if I measured this with a protractor, remember this is sitting on my desktop. If I measured it with a protractor and got 44 degrees, that's what the measure of this angle would be. All right, now if you look at that this one here, it probably appears a lot smaller on your screen right now. So you have 2 different sized triangles, but this is still sitting on my desktop. So this angle is still 44, and this angle is still 44, and this one's still 92. So even though the triangles can appear bigger or smaller, they can have the same angles, the same 3 angles. What's going to be different between the bigger one and the smaller one is the length of the side. So the sides will be up. But the result that we have for similar triangles is that the sides are in proportion. So it's just like we're taking a smaller one and we're enlarging it. So what we can do in similar triangles is we can always write a proportion. And we can say 12 is to 20, 12 is to 20. Since these are oriented, this triangle here is oriented the same way here, we could say that's the same thing as the ratio 3 is to x. So 12 is to 20 as 3 is to x. And you can set up a proportion like this and actually find the missing value of x. And that's what they want you to do here. So in solving proportions, we're going to cross multiply. 12 times x, 12x, 20 times 3, that's 60. And then we'll solve the algebraic equation, divide both sides by 12. So we get x is equal to 5. So that missing side there is what they're asking us to find. Find the missing side. And many times they're calling the missing side. So you set up a proportion using similar triangles and then solve for x. Okay, find the value of x in number 3 and write your answer in the chat or put a question mark like you don't know, you're not sure. Okay, good. So we have lots of answers suggesting 2. 16 divided by 8 is 2, so 4 divided by what is 2? If you write the proportion, you can write it in a lot of different ways. You can write it x over 4, x over 4. Just make sure you do the numbers over in the other triangle in the same order. 8 is to 16. You can solve this proportion and you'll get x equals 2. Here's another one. You can take 4 is to 16, where you're doing this. 4 is to 16. And then you could take the same direction here, x is to 8. And here's another proportion that you could set up and solve. Guess what? X is equal to 2. All right, so similar triangles is another result from triangles that you're going to see in this section. And you're going to be asked to solve some problems kind of abstract like this, but also some applications. It turns out that similar shapes work for quadrilaterals as well as for triangles. So for example, this is a quadrilateral. It has 1, 2, 3, 4 sides. It looks like 2 of the sides are the same, but the other 2 sides are not the same. And this looks like it's smaller than the rest, and you can see it here. So if we took these ratios, 10 over 40, 14 over 56, again, another 14 over 56, and then a 3 over x, if we just kind of link up these corresponding sides and write them as ratios, all these ratios have to be the same. 10 divided by 40, 0.25. 14 divided by 56, 0.25. 3 divided by x, 0.25. So you can just grab two of these, doesn't matter which two, and write a proportion, because the sides are in proportion. And then we're going to cross multiply. 40 times 3 is 120. All right, there are quicker ways to do this if you see the pattern. But it must be the case that x equals 12. Oh, that's right. 3 divided by 12 is 0.25. 1/4. All right, go ahead and find x over here. 7 is to x as 10 is to 90, and that reduces to 1/9. Okay, I see. Yep, x equals 63. Very good. So similar triangles, you're going to see that. You're going to see it both with triangles, and you're going to see it with quadrilaterals. Find x. So this one uses the idea of isosceles and equilateral and so on. It also uses the idea that the three angles of a triangle have to add up to 180. So sometimes the angle is going to appear as the variable x. And so then in that case, you're looking for, like this one down here, you're looking for x, which is the measure of this angle here. Some of these little markings didn't come in that great. Okay, so this one here, what is x? Well, you'll notice that they're marking these two angles. That suggests that these two angles are the same. And in a triangle, if you have two angles that are same, then their opposite sides are the same. So x and 7 have to be the same. That's it. There's no calculation there. It's just noting that we have an isosceles triangle here, so that these opposite sides have to be the same. In number 3, there's a little single mark on this axis here, and a similar single mark on this axis right here. So these two in this big triangle here have to be the same. So if this side and this side are the same, then these angles that are opposite have to be the same. Since these angles are the same here, well, let's see. If we can show that we have similar triangles here, then we can use that fact. But I think what you see here is that since this angle and this angle are the same thing as this angle and this angle, and the three angles of a triangle must add up to 180, then this angle here must also be equal to this angle here. So we have the three angles equal, so we have similar triangles. Not only that, the angles, or the sides, are exactly the same. This side is equal to this one. This side is in both of the triangles. It's in this triangle, triangle 1 and triangle 2. So it turns out, because of the information that they've given us, that our two triangles 1 and 2 are identically the same size. X equals 6. In number 5, here's a side here that's equal to this side over here. So if this side is opposite this angle x, and this angle here is x, then this angle over here has to have the same measure because it's opposite a side of the same length. So this also has to be x, the side opposite the angle. And we know that when we add the three angles of a triangle, we have to get 180 degrees. So what you do is you set up an algebraic equation that you can then solve. It's not too hard. X plus x is 2x. And then if you subtract 40 from both sides, 180 minus 40 is 140. And then finally, if you divide by 2, that missing angle must be 70. So if this is 70 and this is 70, that's 140 when you add them together. If you add that to 40, the three angles add up to 180. Okay, what about number 2? I'll ask for participation now. So go ahead and put your answer to number 2 in the chat. Two main ideas in this worksheet, and that is the sum of the angles have to add up to 180. And the other thing that's significant is that angle, if you have a triangle where two angles are the same, then their opposite sides are also the same. X equals 6. These two angles, it's indicated because they put just a little marking there, that these two angles are the same, so their opposite sides must also be the same. So 6 and x must be the same. What about number 6? What's the value of x? Go ahead and write your answer in the chat. Okay, good. Again, these markings here mean that these two sides are the same, have the same length. So that means that the angle opposite those must also. So the 75, which is the angle opposite this side, must be the same as x, 75. Oh, okay. Well, let's move to number 8 now. Still have x and 75 in there, right? Different orientation. Okay, very good. Same idea that these two sides are the same. So if you look opposite, those two angles have to be the same. Well, we know this one's 75, so this one must be 75. 75 and 75 is 150, so the missing side, or the missing angle there, must be 30 degrees. Okay, let's go to the Pythagorean theorem. And the Pythagorean theorem is a theorem inside a right triangle. that if you have a right triangle, and all that's required is you have a right angle and you have a triangle. So you have three sides connected together where one of the angles is a right angle. Then if you label the sides with just some variable names like this, A, B, and C, X, Y, and Z, it turns out that if the sum of the square of the two legs of a right triangle is equal to the square of the hypotenuse. So if you take one leg, X, and square it, and then take the other leg, and by leg I mean non-hypotenuse. So there's two legs and then there's the hypotenuse. And the hypotenuse is always the largest side of a triangle because the largest angle is going to be 90. You can't have one 90-degree angle in a triangle and then have another angle that's even larger because the sum of the three angles have to add up to 180. And if you have 90 here and you have some other angle that's 92, let's say, you've already exceeded the 180 degrees. So the largest side in a triangle is the one that's opposite the right angle, and it's called the hypotenuse. All right, and then the theorem says if you take one leg and square it, take the other leg and square it, and then add those two together, the sum of those two is going to equal the hypotenuse squared. So that's it. So the first couple of problems here, and it goes both ways. If this relationship holds, then you have a right triangle. So in this first one, it says, do the following lengths form a right triangle? Well, the largest side is 9. So since the largest side is 9, it has to be the hypotenuse. And so in order to confirm that this is a right triangle, we would have to take 6 squared and 8 squared, add them together, and then if the sum there is equal to 9 squared, then we have a right triangle. And if those two sides are not the same, then we don't have a right triangle. So even though this one looks like a right triangle, 6 squared is 36, 8 squared is 64, and 9 squared is 81. And we know that 100 is not equal to 81, so we would say not a right triangle. Now this one is similar, but if we took 6 squared and added it to 8 squared, we would in fact get 10 squared. So this is a right triangle. 36 plus 64 does indeed equal 100. What about number 2? Is 5 squared plus 12 squared equals 13 squared? Is this triangle here a right triangle? 13 is the largest side. If you take 3 squared and add that to 4 squared, do you get 5 squared? Well, these are the equations that you have to write, and then just do the arithmetic to confirm that they are equal, both sides, in which case you have a right triangle, or they're not equal, in which case you do not have a right triangle. This one works out. We got 25 plus 144 is 169, and 13 squared is 169. So yes, a right triangle. And 3, 4, 5 is also a right triangle because 25 is equal to 25. All right, now this relationship where one leg squared plus another leg squared equals the hypotenuse squared can help us, as they say, solve a triangle. And what they're asking us to do in these problems down here is just to find the missing side. So if you like, you can just label the missing side X and then try to find X. All right, so many of these are going to work out so that you don't have a nice whole number answer. So we'll round them to the nearest number of decimal places. But let's take a look at one like this. Here's the right angle, and the side opposite that right angle is X. So X is the hypotenuse. So X is the largest. So if we find X, it has to be larger than 8 because 8 is currently the largest side. This also tells us that we have to take 4 squared and 8 squared and add them together because those are the two legs. And that's going to equal the hypotenuse squared. All right, 4 squared is 16 and 8 squared is 64. And when you add those two numbers together, you get 80. So X squared equals 80. Now they're going to want to know what the missing side is. And so you have to somehow figure out what X is, not X squared. And the way we do this, it would be nice if this was 81. If X squared was 81, then we would have X is 9 because 9 squared is 81. But what we're going to do here is we're going to take the square root of both sides. If you take the square root of a square, you're just left with the X. And if you take the square root of 80, we would write that the square root of 80. We know the square root of 80 is very close to the square root of 81, and the square root of 81 is 9. So therefore, the square root of 80 is going to be a number very close to 9. The square root function is right above the x squared, right there. X squared, square root. So you have to hit the second key and then x squared, and then 80. So we know this is going to be 8 point something, right? Close to 9. 8.944. So you may be asked to give the decimal approximation, or you may be asked to give the exact answer as a square root. Either are correct, both correct answers. This is what we call the exact answer, the square root version, and this is the decimal approximation. And notice the hypotenuse, 8.944, is a little bit larger than the largest leg. All right, a problem like number 22. Now for number 22, they're giving us an x, and the x is not the hypotenuse. So here's the right angle. So the side opposite the right angle is the hypotenuse. So x, this x that we're looking for, it actually has to be a little bit smaller than 6.5 because it has to be smaller than the hypotenuse. To find it, we're going to use the Pythagorean theorem. We're going to take one leg and square it, and we're going to take the other leg and square it. And when we add those two together, we're going to get the hypotenuse squared. So square, 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 and then add the two legs together, and that equals the hypotenuse. 2.7 squared is 7.29, and 6.5 squared is 42.25. So sometimes the numbers can get messy. That's okay, we can deal with it. I want to solve for x, so I'm going to get the x squared by itself. I'll subtract 7.29 from both sides. I'll get rid of these. And over here, this is 34.9. Right, so now we're going to take the square root of both sides. If you take the square root of x squared, if you just think about it, if you start with 3 and you square it, you get 9. If you then take the square root of 9 is 3. So the squaring and then taking the square root, you start with something, you're going to end with the same something if you apply those two operations together. So if x is already squared here, if we then take the square root, we're left with x. And then we have the square root of 34.96. Now this is going to be a little bit less than 6 because we know the square root of 36 is 6. So the square root of something a little bit less than 36 will be a little bit less than 6. 5 and some change. And we'll use the calculator to come up with the decimal approximation of 5.913. And then we're going to reflect back and we're going to notice that, okay, can this side be 5.913? Well, it can because 5.913 is smaller than 6.5. Pythagorean theorem. All right, so why don't you try number 21? Sorry, that doesn't look that great. I'll zoom in a little bit. All right, so find it. Here's the right angle, and this side is 5.3. And then we're missing this side here. So when you first look at this, you should ask yourself, what kind of an answer am I expecting? Is it going to be an answer larger than 8? Is it going to be a number less than 7.2 or greater than 7.2? Is it going to be greater than 5.3 or less than 5.3? All right, someone's already there. Generally, if, and when you're doing the problems online, round to the number of decimal places that they ask for. But generally, if they've rounded their numbers to the nearest tenth, then we can round our answers to the nearest tenth as well. If you want, you can round it to more places, 2 places or 3 places, but you just should have more than just, you should have 1 or more, ultimately. Okay, so I see one answer that I know can't work, but I'm not sure that that's the answer to this one. Okay, so she took it back. Yeah, so here's the right angle, and 7.2 is opposite. So 7.2 has to be the largest side. So you're looking for something less than 7.2. So some of you are coming up with 5.3. So you're saying that this is isosceles then, because this side's 5.3. Okay, so we have 5.3 squared, that's one leg, plus the other leg, and the other leg in this problem is the f, and that has to be equal to 7.2 squared. Errors that students make a lot, or they just forget to square one of the numbers, for example. So 5.3 squared, calculator for that, and 7.2 squared, 51.84. Now, before you take the square root, you want to get the x squared by itself. So we're going to subtract 28.09, and that's going to give us 23.75. If you're going to round on these problems, only round the very last answer. So never round like intermediate results. So for example, I wouldn't want to round this to just 28. I want to leave it at 28.09. And I wouldn't want to round this to 51.8. leave it 51.84. All right, now we're going to take the square root. Oh, okay, so now I see some 4.87s. So probably the way that we would report this would be 4.9, just to round everything to the same number of decimal places. Now, some students will just report the answer as 23.7. Now, I know that the answer cannot be 23.7. It's an impossible, because I already know that there's two sides here. And imagine that if you had like pieces of sticks or something that you were joining together, it has to be the case that these two sides, when you add them together, they have to be larger than this. I'll try to draw a triangle here. And my question is this triangle possible? Could I actually draw one like this? So let's say that this is 13. This one's a little bit bigger. Let's say it's 20. And this one is much bigger. So let's say it's 37. Is this a right triangle? I see some no's. So this is the largest side. So you'd have to take 13 squared plus 20 squared and see if it equals 37 squared. We've done some like this. Here's my next question. Is this a triangle? And the answer is not a triangle. That's right. Even though it looks like a triangle, it's not a triangle, because if you added these three sides, let's say we had 37 down here, and you had, let's imagine that here's the side 13 that we're going to let kind of rock back and forth. And we're going to rock this one back and forth until it joins this one over here. That's a little bit larger, 20. Well, I think I drew 20 too large. But let's say that's 20. And let's say that's 13 right to there. Now, if these two sides can rotate at these points, and we can just move them back and forth, and this one can do the same here, and they can rock. If we took this one all the way back so that here's 13, and then we took this one, again, I drew it out of scale, and we let this one go all the way here, it would hit here. These two legs here wouldn't join up in the middle, because 20 plus 13 is 33, and we'd still have a gap in there of 4 that we could not bring those last two legs together. So this is drawn as a triangle, but it's an impossible triangle, because when we add these two sides, we get something less than this one. Okay, let's take a break, and when we do, I'm going to set up the project. So it's probably a good idea, if you don't have it printed out, that you go print out the project. It's in e-learning, and we'll come back at 3:52. Define some of these angles that you're going to see in a regular polygon, and then maybe go through and fill out some of this. Now, we have all kinds of different polygons. For example, if we have, triangles, lots of different triangles, like this, right triangles, non-right triangles. There's only one regular polygon. And when it says regular, what it means is that all of the sides have the same measure, and all of the we call them vertex angles, have the same measure. So the triangle that has all angles equal and all sides equal would be this equilateral triangle. So we have a lot of different triangles, but there's only one that's the regular triangle. The equilateral triangle is equal to the regular triangle. There's a regular quadrilateral, there's a regular pentagon, there's a regular octagon, there's a regular septagon, octagon, nonagon, decagon, dodecagon, and so on. But what's key about regulars is that all three sides are equal and all three angles are equal. In a quadrilateral, if we want all the four sides to be equal and all the four angles to be equal, there's only one shape that meets those conditions, and that is the square. So the square is equal to the regular quadrilateral. So there's lots of, you've got rectangles, that's a four-sided figure, so therefore that's a quadrilateral. You've got kite, where you have two sets of adjacent sides, that's a quadrilateral, but different side measures. In a rectangle, the opposite sides are equal, but not all four sides are equal. It's only in the square where we have four angles are equal and all four sides are equal. So this is the regular quadrilateral. And you've probably, learned a lot about other quadrilaterals like this one, a parallelogram, or maybe even this one here, which is a trapezoid. All of these are quadrilaterals, This is the regular quadrilateral. Okay, so that's what we're talking about on this worksheet, are regular polygons. A polygon means various, geometric, two-dimensional geometric shapes that have a variety of side lengths. So you can see the lengths of the sides here. So over here, I will draw a picture of each one of the angles. Angle A is a central angle. Now this is a 1, 2, 3, 4, 5-sided shape. And a five-sided shape we call a pentagon. In fact, we have a governmental building that looks just like this from the sky that is called the Pentagon. And this is a regular pentagon. All of these sides are equal, and so all of these vertex angles are equal. Now the central angle, imagine that you put a dot right in the middle, and that would be, say, we'll just call it the center. Then connect the center to two adjacent vertices of the pentagon. So it doesn't have to be these two, it could be these two down here. But anyways, connect them. This angle right in here is called the central angle. And it turns out that in addition to having 5 vertex angles and having 5 sides, this also has 5 central angles. And these 5 central angles, 1, 2, 3, 4, 5, all have the same measure. So there's a lot of symmetry in these shapes. So when they talk about vertex angles, when they talk about central angles, they're talking about these angles that are in the center of the shape that are formed by connecting the center with 2 adjacent vertices on the outside of the pentagon. Now, if we know this, then we also know that as you go around this circle, all the way around, if I start here and go all the way around and stop there, that's 360 degrees. And so I can actually figure out the measure of each one of these angles because they're all the same. We have 1, 2, 3, 4, 5 equal copies of the angle A. So 5 A's has to equal the entire distance around, 360 degrees. If you divide both sides by 5, you can figure out what the measure of one of those central angles would be, 72 degrees. So if one is 72, then they're all 72. And if you take 5 times 72, you get all the way around the circle, 360 degrees. So what do we know? The pentagon has 5 sides, and we just calculated the measure of the central angle to be 72 degrees. So 72 is what you want to go in that spot right there. All right, the next one, or maybe I should just do the C. C is a vertex angle, sometimes called an interior angle. But here it is, that angle right there, formed by 2 adjacent sides, is called a vertex angle. And again, it turns out that there are the same number of vertex angles as there are sides, 1, 2, 3, 4, 5, 6. So this is a regular 6-sided polygon, and the 6-sided polygon is called a hexagon. So all the central angles are the same, all the sides are the same, and all the vertex angles are the same. But that's what we call a regular hexagon. Now, before we go and calculate this one, I want to show you something else. Let's go look at the exterior angle. This is a regular triangle, or an equilateral. We have a special name for this one. Now, the exterior angle is on the exterior. It's not actually inside the shape itself. So what we're going to do is we're going to take one of these sides and just extend it over like this. And this angle here on the exterior is called the exterior angle. It's not actually an angle inside. If I drew the exterior angle down here, the exterior angle would be this one. So one thing that you know is that the sum of those 2 angles, since they fall along a straight line, that if you took angle C and you added with angle B, they have to add up to 180 degrees. So if we could figure out angle C, which is the vertex angle, or we could figure out angle B, which is the exterior angle, we could find the other one. All right, so let me show you how we would figure out what that. I'm going to try to draw a hexagon here. All right, so looks something like this. We also know that there's 360 degrees around, and there are 6 different interior central angles here. And so each one of these would have to be 60. 60, 60, 60, make up 180, and then another 60, 60, and 60. So for the hexagon, the central angle is 60 degrees. For the hexagon, the measure of the central angle is 60 degrees. All right, let me extend here, and here's my angle B that I'm looking for. Now it turns out that, in this little triangle here, that these two are the same size. They go from the center out to a vertex. So these two angles have to be the same, whatever they happen to be, they're at. And if the three sides of the triangle in here have to add up to 180 degrees, we already have 60 accounted for, then these two, when you add them together, they have to be 120 degrees, but they're the same. So these angles here are also 60 degrees. So each one of these triangles in here is an equilateral triangle. So this is 60, and this is 60, and this is 60, and this is 60, all the way around 60. Well, we also know that along a straight line, that the number of degrees is 180 degrees. So this blue angle here, this 180 degree angle, is made up of this 60, and this 60, and this angle B, the one that we're looking for. And so the only thing that B can be is 60 degrees, so that when you add these three 60s, you get to 180. So in this hexagon, this exterior angle is 60 degrees. For the hexagon, the measure of an exterior angle is 60 degrees. Now, as soon as we have the exterior angle here, this angle here, and this angle here, and this angle here, and this angle here, these are all vertex angles. You add both of those together, you get the vertex angle. So for this hexagon, the vertex angle is 60 plus 60, or 120. So the measure of the vertex angle, 120 degrees. Now, the last thing that you're going to want to do is this one here, because it can help you with some of the formulas you're going to see later. Again, we're just doing this entire hexagon problem here. But the sum of the vertex angle, if this is one vertex angle, 120, we have 1, 2, 3, 4, 5, 6 of them. We have 6 vertex angles. So if we wanted to add up the sum of all these vertex angles, you could just take 6 times the size of the vertex angle, which is 6 times 20, 120, so 720 degrees. Here's the equilateral triangle. Maybe I'll do 2 or 3 rows of this, and then I'll set you off on completing the rest. All right, so here we have 1, 2, 3 equal angles, and if you take 360 degrees and divide by the 3 angles, then each one of them would be 120 degrees, central angle. We know the vertex angle is 60 degrees. There it is there, 60. And then B is the vertex, or the exterior angle. So if this interior angle is 60 and the distance from here to here is 180, then B, the exterior angle, must be 120 degrees. So 120 degrees for the exterior angle, for the equilateral triangle. The vertex angle, we know for an equilateral triangle, is 60 degrees. And in this case, we have a triangle. If we sum up these 3 angles, 60 and 60 and 60, we get 180. And we knew that. The sum of the angles of a triangle is 180. But notice that's just 3 times 60, 180 degrees. Of course, 3 sides. A square has 4 sides. The vertex angle, 90 degrees. We know that in the corners there, those angles are 90 degrees. If you do the central angle and you put a dot in the middle, you have 4 equal angles in the middle, 1, 2, 3, 4, and that has to make up 360 degrees. So those central angles here are also 90 degrees, and they even look like they're 90-degree angle, right angles. If in the corner we have a 90-degree angle, and here's the exterior angle, this is our B. If it's 180 degrees all the way around, and this one is 90, well, the exterior angle there must also be 90 degrees. So for the square, the vertex angle, the exterior angle, and the central angle are all the same. They're all 90 degrees. Now we have 4 different angles. If each one is 90, the sum of the vertex angles would be 90 times 4, or 360. So we saw that the central angle was 90 degrees. We saw that the vertex angles were 90 degrees. And we saw that the exterior angle was 90 degrees. Then when we added up our 4 exterior angles, we get 360. Now, what's more important than just looking at each of the individual rows is to look at the relationships between the different columns. What did we do with the central angle? Well, we said there's 360 degrees around, and we need to divide that into the number of sides. For a square, 360 degrees around, and we had to divide it by 4 because there were 4 central angles that made up that 360 degrees. For a pentagon, we took that 360 degrees and divided it up in 5 equal chunks. And for a hexagon, we took the 360 degrees and divided by 6, so that each one is 60. So you definitely can see a pattern on how you might deduce all of those numbers in that first column. Then I would ask you to look at the relationship between the central angle that we've already calculated and the exterior angle. The central angle and the exterior angle. Central angle and, sorry, you can't see it. Look at the numbers in this column compared to the numbers in this column. Maybe that would suggest another relationship for you. What do these numbers have in common? Now we can see that they're increasing as the number of sides increase. Well, what's the relationship between the central angle and the vertex angle? Central vertex, every single time. Those are the patterns that we want you to see. Okay, let's take about 15 minutes and I'll put you into groups and let you work through this. I don't have a Google Doc for this. And so what you should do is just to get together and talk about these. And what's going to be a little tricky is the formula down at the bottom. What if you have just n sides? Can you deduce what the relationships, and all of these are going to be formulas. So hopefully you can use the information above to come up with the formula. All right, so 15 minutes, I'm going to ask somebody in the group to share and then talk about as much as you can filling in this document. And everybody should turn in their own copy, although for the next 15 minutes, you'll be able to work in groups on getting it correct. So as much as you can complete in 15 minutes, and then the rest you'll have to complete on your own. Okay, here comes the group, 15 minutes. All right, it looks like the rooms are already formed from earlier, so I'm just gonna open up the same rooms and you get to work with the same folks. So there's one additional section that we're going to be looking at, and it gets into area and perimeter, though we'll see perimeter in a lot more detail later on. I've given you the formulas that appear. These are area formulas. For example, the area of a rectangle is length times width. And so the way that we would do that is if you had a rectangle that had 1, 2, 3, 4, so this side is 4. And let's say this side is 2, and you wanted to know what the area is. Well, the area conceptually is just the number of these unit tiles, 1 by 1 tiles, that you would need to cover up the entire space. So the number of these that you would need to cover up the entire space would be 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 tiles that would cover up this rectangle. So therefore the area is 8. And notice that if you just take 2 times 4, you get 8. All right, I'm not going to recite the formulas here. I will assume that that you can do that. What's interesting about some of these is that here's your height, and if you just took and cut this one here, so that this is the height, and this is the height, and you chop this one off and brought it over here, then this side right here is the same as this side down here, but this side is in our new rectangle. So here's the base, and here's the height. So the area is base times height. So it's the same exact formula as a rectangle, but you have to cut off a piece over here and bring it over here in order for it to look like a rectangle. What's interesting about triangles is that the height doesn't have to appear on the inside of a triangle, and so the height is the perpendicular distance from the base up to this other vertex. So if I have say that this is the base, and let me put a base from here to here. So let's say that in every one of these triangles that I'm about to draw, every single one of them, this is going to be the base, and then this over here is going to be the height. So here's one such triangle, base times height. So there's one triangle. If I use the same base and I bring and say, over here is my next point, and here is my triangle, right there, same base, but now the height is on the outside of the triangle. This is triangle number 2. If I draw a third triangle, here it is, same base, but then I put it way over here and I connect like this, and here's the height. Again, it's outside of the, maybe I'll draw one more. Let's draw this one here. There it is, the black one. And the height here is on the inside of the triangle. But in every single case, the base, I used this base as the lower side, kind of the flat side. The red, the black, the blue, and the green triangle all have B as their base, and they all have the height as being H. And so even though these triangles look dramatically different, every single one has the same height and base, and therefore their areas are identical. The area inside the green is equal to the area inside the red, is equal to the area inside the blue, is equal to the area inside the black. All of them have the same area. The formula is 1/2 base times height. And of course that comes from, if you have a triangle like this, that you can form a parallelogram that looks like this. Here's your base, and here's your height. And we know that the parallelogram has an area that's equal to the base times the height. And so this triangle is exactly half of the parallelogram. So the area of the triangle is 1/2 the base times the height. And that's where that formula comes from. Okay, a trapezoid is similarly two triangles that we add together. They just have different bases. So, well, here's the formula. I don't want to spend a whole lot of time on it, but if you take a look at this, this is B1 up here, base 1, this is base 2 down here, and here's your height. So what is the area? Well, what we do in this case is we cut this trapezoid in half, and then we add the areas of the two triangles. So first, let's do the area here of this triangle down here. It's a triangle, so it's 1/2 times the base, and the base is B2 times the height. Well, here's the height. And this triangle up here is also, we call this area 2. It's also 1/2 times the base times the height. But the base up here is B1, the base of this triangle. B1, and then the height is always perpendicular to the base, so the height is also. So if you take the area of the lower triangle and add it with the area of the upper triangle, they form the trapezoid. So the area of the trapezoid is equal to 1/2 base 1 times the height, this one, plus this one, 1/2 times the second base times the height. And through a little algebra, if you take out the 1/2 and you take out the h, 1/2 and the h, what's left is B1 plus B2. So that's how you get the formula for the area of a trapezoid. And you'll have, when you're doing problems on the exam and homework and so on, you'll have access to, instead of B1 and B2, they called it A and B, but same idea. Area. Okay, now the more interesting problems are the problems where they involve multiple shapes. And so what you're given typically is a shape that looks like this, and then you're asked to figure out, what is the area of this irregular shape. So usually it involves putting together a couple of geometric shapes and adding them together. So let's take a look at this one and pay particular attention to the unit. So all of these are in centimeters, and that's the one thing that you should note, that they all have the same unit attached to them. All right, I'm going to take this one and I'm going to draw a vertical line going right straight down. And the way my strategy here is I'm going to figure out the area of the rectangle, and then I'm going to figure out the area of the triangle, and then I'm going to add them together to get the area of the whole thing. So first I'll call this one the area of the rectangle, and this one I'll call the area of the triangle. The area of the rectangle is length times width. There it is there. Now, a couple of things, that if this length up here is 6 centimeters, then this distance right here is also 6 centimeters. And if this whole side is 9, then this smaller little chunk over here must be 3, because you have to have 3 and 6 add up to the whole thing, 9. You see that okay? Similarly, the triangle stops right there. We know that this is 3, and we know this opposite side over here is 10. So this piece of the vertical side must be 7 centimeters. 3 and 7 has to equal the 10 over here. 6 here, 6 here. Since this whole thing is 9, this little chunk of the triangle is equal to 3. All right, so continuing along, now that we have the dimensions that we need, this rectangle in here has a width of 6 centimeters and a length of 10 centimeters. So in terms of units, multiply the numbers to get 60. But then you know from our work in unit analysis that centimeters times centimeters is centimeters squared. So we're going to have 60 square centimeters would cover that area. And then the area of the triangle, well, that's 1/2 times the base times the height. That's our formula. And we're looking at just this little triangle here. We know that this is a right angle, this is a right angle, this is a right angle. So therefore this is a right angle, therefore this is a right angle. So we know we do have the base and the height being perpendicular. So the base is 3 and then the height is 7. And these are both centimeters. So when we and the 1/2 doesn't have a unit attached to it. So when we multiply centimeters and centimeters again here, we're going to get square centimeters. All right, 3 times 7 is 21, divided by 2 is 21/2, which is 10.5. All right, so the final answer then, you would take the 60 from the rectangle and the 10.5 from the triangle, add them together, and then we would say the area of the whole thing then is 70.5 square centimeters.